So it really is a very great pleasure and nostalgic for me to introduce and welcome Professor Balachandran to give this talk at my father's centenary. So I was in 1959 when the theoretical physics seminar started. I was 4 years old, but I do remember the flow of students in my house going upstairs to the lecture hall, and in particular, I remember Professor Balachandran coming and attending these seminars. So my memories go back to 1959. And I also remember my father talking in very high terms about some of the bright students in the seminar, and one of them being Balachandran, and how proud he was that he got this postdoctoral fellowship in Chicago. That's why I mentioned this yesterday. So I'm very happy that he's here at this conference, and he's going to talk about confinement and deconfinement in gauge theories, a quantum field theory.
Thank you. Well, just as a remark, I have known Krishna since he was knee-high to a grasshopper, very tiny. So it is a long association we have had. But I will go to my talk right away. There was a problem in preparing the talk because of first the time scale, and then I realized that it will be a mixed audience, so I did not exactly know what I should talk about. Okay, my interests are nowadays more close to algebraic quantum field theory and von Neumann algebras and their applications to physics, and it did not seem exactly suitable for a mixed audience, which I guessed would also have a number theorists who are not exactly tuned to, maybe not tuned to this kind of topic. Okay? But in any case, I will try my best. That subject I am going to present, I am a physicist, so I want to talk about physical phenomena which are affected by the fact that we are dealing with quantum field theory, where the number of degrees of freedom are, well, I don't know what is meant by degrees of freedom, but it involves quantum fields on space-time, which are operator value distributions, whereas and that fact that they are operator value distributions have physical consequences. Okay? It is not an abstract statement, but it has very strong physical consequences. For example, the proof of the spin statistics theorem, the PCT theorem, and even scattering theory necessarily involve these facts, which are basic, which apparently we can only derive from quantum field theory and relativistic causality. Okay? At least I don't know of any other derivation which can access these facts. Okay? So that is why I got it personally interested, and I want to, in the course of the investigation, as time progressed, I got involved with superselection rules, which are essentially the inequivalent representations of von Neumann algebras, okay, or let us say local field of operator algebras of quantum field theory, which it turns out are actually uncountably infinite in number. Okay. So people have thought that they were irrelevant, but now we know quite clearly that that is not the case. There are very clear physical consequences, and that was my attraction to this field. And I want to tell you what I know, why that was our attraction to this field, which slowly developed over a period of time with my collaboration with many people, including especially Sachin Vaidya in IISc in Bengaluru, Parameswaran Nair, who is in City College, and some others, okay, some Sasha Pinzul, who is in Brasilia, and so forth. So we have been talking about these matters, and slowly some ideas developed, and I will try to present it, and for sure I will finish before 1 o'clock, so we can go for lunch. Okay? So I will simply stop at some point. Okay. So I have picked a topic where at least there are some sentences which will be of attraction to people who are listening to me. Okay? So what I want to do is to present to you a new mechanism for confinement, deconfinement transitions in quantum field theory. Okay. So the model I am presenting is quite physical. Okay. At least to me, they are quite physical. But that may be because I have brainwashed myself by working with this field for a long time. Okay. So, but in any case, I'll present it to you, and you can make comments or make suggestions. It does have one point is that what I present has physical consequences. In physics, we don't accept things unless they are supported by evidence, and here we do, but there are clear physical consequences of what I said, what I say. Can they be experimentally checked? That is like gravitational radiation. It doesn't seem accessible now, but maybe later. Okay. It does have consequences for infrared divergences, in which people like Ravi are deeply interested. So I'll try to present them to you now. Okay. So let me see here. Here there is some stuff here. So by way of introduction, I can tell. So these are my the summary paper which appeared last was consisting of these people, which surveyed our activity in the case of QCD. It is fairly detailed, and we found that many structures with which we are not very familiar, for example, things like Kunz algebras, Caesar algebras and their completions, all these things started coming in. Okay? So to us it was quite fascinating, and they are described in this paper. Okay? So let me go on. There is a review of our earlier work, especially all this is centering around the Gauss law. The Gauss law, we think, is a casual thing about the conservation of electric charge, but we know for over a period of time that it goes far beyond that. Okay? In particular, long ago, I should say here, it has already been recognized by people like Froelich, Morchio, Strokey, and many others, that because of the Gauss law and this proper treatment as an operator equation, not as classical equations which you stuff into functional integrals, do some manipulation, these people proved in the context of quantum field theory that because of the treatment of the operators which come in the Gauss law as operator value distributions, they proved in a rather long but very precise paper that Lorentz invariance is broken. Okay? They proved that Lorentz invariance does not act, changes the superselection sector and cannot be implemented within a given irreducible representation of the local algebras. So Lorentz invariance will be broken, and it is coming because of the fact that the infrared cloud that is surrounding each charge particle is very characteristic of that the process of producing that charge particle. And what happens with the Lorentz group is that it changes the cloud. Okay? When you change the cloud, which are infrared effects, they change the superselection sector and cannot be unitarily implemented. So this Lorentz transformations then become intertwiners between different representations of the local algebras, and later on they also, well, one can also imagine, I will try to give some physical consequences of this fact, okay, of what this implies. Okay. In the same context, when we got, by the way, there are results of this kind already in the context of quantum gravity by Abhay Ashtekar and Anmanon Ashtekar and his collaborators, who have discussed asymptotic quantization and quantum field theory, and they have also come across these features in their earlier papers, okay? But in the context of quantum gravity. But later, working with Sachin Vaidya and I think Sechkin Kucholu, we found out that this thing happens also in QCD. We prove, and that I will give you now, an argument which I think is quite strong, that QCD is spontaneously broken. Okay? It cannot be implemented because it is a non-abelian group. Okay? The QCD group is an asymptotic group, and because it is the fact that it is a non-abelian group, we cannot implement it in a given irreducible representation of the local algebra, which are the accessible gauge invariant operators of the theory. Okay. So now let me start here. Forget about space-time. I will not do mythology saying that there are space-time is 11 or 10 dimension. I will do 3 plus 1, and I will choose a standard metric. Well, I will choose a metric which I have written down here, and the gauge group I will be dealing with here is the group of maps from space-time into this into a compact Lie group. Okay. It's quite important that we are dealing with compact Lie groups. So compact groups can be discrete, but at least let us say compact Lie groups. So the gauge group is not a group in the standard sense; it's a group of maps. Okay. So an element of the gauge group G, which I have written down as script G, okay, element of that group G will be some function which G of x, element will be a function on space time with values in this compact group G of x. So it is a map of this kind, and as the coordinate x goes to infinity, it will approach some fixed, some particular element h of a unit vector in the direction in which you go of this compact group. So in principle it can take different values as you go to asymptotic limits in different directions. There is no reason why it should go to the same value, but normally we take it to be in the standard way of writing QCD, we assume that the limit is constant. But then there is also some statement that asymptotically, yeah. So the people say things like, I'll come to that, come to some further things. Now there is some limit, already there is some limitation here, because there is no physical reason why it should approach any limit at all at infinity. Nothing in quantum field theory says that this G approaches any fixed limit as you go to infinity. I don't know how to deal with that case. It is allowed, it is apparently allowed, but I don't know how to deal with that. But maybe as time progresses, we will have insight into that. If it does approach different, if you do have a case like that, I think that the different limits you choose here, we will define different supersolution sectors, and we will see that I suppose that if the limit does not exist, but it depends upon how you go to infinity, then I guess that the corresponding supersolution operators will characterize different irreducible representations of the local group. Okay? But this I don't know, but I suppose that is the case. Okay? So here what I want to do is to propose a new mechanism for confinement deconfinement transitions. Okay? This is not the kind of things that people do with Wilson lines and so forth. I am not doing any activity with functional integrals, but I will give a physical argument why there are confinement deconfinement transitions built into the quantum QCD already. Yeah. So let me see how I go. Yeah. So this is telling you the, yeah. So this is by way of notation, my connection form is a QCD I will be dealing with. So my connection form A mu is a connection, Lie algebra valued connection A mu, which in quantum field theory will be a distribution. Okay. So and the canonical conjugate variable will be E mu, electric field with upstairs indices. Okay. What happened now? Yeah, with upstairs indices, and I'll choose a basis for the Lie algebra of SUN in the defining representation as lambda alpha. Okay. So lambda alpha is normalized in the standard way, where this lambda alpha are n by n matrices in the defining representation of A mu. So A mu can be written like this, and E can be written in the other way. Okay. Now let me come to Gauss law. The actor in this whole business of superselection rules is the Gauss law. Okay. There are other cases where Gauss law is not playing a role. For similar analysis can be carried out for example, ferromagnetic transitions or for superconducting transitions. It has been done actually by people doing algebraic quantum field theory in various ways, but I will not deal with them. Okay. So they, they are not related to gauge transformations, but some other related effects. For example, old papers of HEP already deal with it, okay, but I will not touch that. So let me go back and write down the Gauss law. I will write the Gauss law not as a divergence, covariant divergence of the electric field plus J0, okay, equal to 0. I think that equation makes no sense, okay, in quantum field theory, because E is an operator value distribution, and what is the meaning of saying that the operator value distribution is 0? Okay? Does it act on a quantum state? The quantum state is an element of a vector state, is a element of a Hilbert space. What is a distribution acting on a Hilbert space? We don't know. Okay? At least I don't know. So what we do normally is I'll multiply it by test function cascade, psi. Where psi is a test function which is Lie algebra valued, and let me assume for a minute that this test function is C infinity and compactly supported. So the Gauss law will be written like this, where the test function can take all possible compactly supported functions. So then this makes more sense, because I am smearing the Gauss law, standard Gauss law with a test function, and then I get an operator, and I can imagine that acting on a quantum state, and I can say that this operator acting on the quantum state vanishes. So that will be, I have a huge Hilbert space where all kinds of things are acting, including quantum fields like spin half field or colored fields. They will act on the they are called the field algebra. They generate what are called field algebras. They will act there. The Hilbert space is an enormous separable Hilbert space. Okay? But this will operate. This vanishing of this operator on the quantum state will pick out a domain for the operator algebra, the observable algebra I am dealing with. So this is picking out an appropriate domain for these operators. Domain issues cannot be avoided in this kind of analysis. So this is picking out a domain for the operators I am dealing with. Okay? Well, here is by way of a notation, the bracket here, the two ends, is just to denote the trace. Yeah. And psi is a Lie algebra value test function. And I will assume for a minute that this psi, which I can write as psi alpha lambda alpha, where psi alpha are functions, I will assume, okay, yeah. So I will assume that these test functions go to some fixed, I will assume that they have limits as x goes to infinity, and become functions of the unit vector as I go to infinity. As I said a minute ago, I don't know why I should assume that, but I will assume that, because otherwise I don't know how to deal with the problem. Okay? So since I am running over all test functions, this is true for every compactly supported test function. So the Gauss law then is interpreted as smearing the classical Gauss law with test functions which are compactly supported and C infinity. So, and the Gauss law is the statement that acting on the quantum, the Hilbert space, they pick out a domain. That is, we look at the subspace of the quantum Hilbert space where these things vanish. Yeah. I would like to write this not in the way I have written down, but after partially differentiating and putting the covariant derivative on the test function. Yeah. This is important. For example, if some of you are familiar with Sobolev spaces, the way PDEs are treated, partial differential equations of elliptic operators are treated, this is quite canonical. Okay? If you give me an elliptic operator on, say, on a manifold with the boundary, if Kesavan had been here, he would have appreciated maybe. Okay? Where you smear it with test functions and take the differentials and on the test functions. This gives you much greater flexibility in dealing with, there are distributional solutions of these equations, and they can be handled by doing this activity. So that's what I am doing here, and shifting the derivative to the test functions. Okay? Then the statement I had made previously regarding Gauss law vanishing on the quantum states will be the statement that this operator, which is the same as the previous one classically, where I have done a partial integration, but I want to look at it as an operator equation on quantum fields, as an operator acting on a Hilbert space, and this object here then vanishes on the Hilbert space, not the Hilbert space, on a subspace of the Hilbert space, which defines a dense domain in the Hilbert space for the operators of the theory. Domains are dense, but they are the operators of many different domains. The Hilbert space is a infinite dimensional separable Hilbert space. It's an awful object. So all kinds of things can happen, it do happen, and this is picking out a domain. Now, so I take this as vanishing on the quantum states, but suppose once I am given this equation, the possibility arises that I also consider test functions cascade which do not vanish at infinity. We will see that this is quite important. If that is the case, so those things where this psi does not vanish at infinity is not Gauss law, but we will see that they define charges, and they are operators with which we do deal with in quantum field theory, and they are non-vanishing on. They need not vanish on the quantum states. So when they do not vanish on the quantum states, they define the charges of the theory. For example, if the psi goes to a constant at infinity in QED, this object here becomes electric charge, and is non-vanishing on the quantum states. Is a statement that we are dealing with a electric charge state for the domain of my operators. There are also cases where the psi approaches non-zero functions at infinity. So that will mean that the moments of the electric charge and the charge density at infinity do not vanish on the quantum state. So it is saying that there is a spread of these charges at infinity. Okay. So now the important thing is that now we know that the Gauss law commute with all local operators. So when the psi vanishes at infinity, this is simply another way of writing Gauss law, and the statement would be that they commute with all local observables. Because of locality, we have argued many times and also before me, for sure, Raphael Sorkin and Friedman and Sorkin have written several papers where even when we remove the test function condition at infinity, so they are no longer Gauss law, they still commute with local operators because of the fact that because of locality. The commutation relations, the algebraic structure, say the fact that E and A are canonically conjugate is a local equation, and the locality then implies that they commute with these operators, even though I have taken away the condition that psi goes to 0 at infinity. For example, as I told you, if I think of this equation as, what is this? Let me introduce you what it is. If psi were a constant at infinity, I can do a partial integration. So I can write E dot ds. Psi goes to, suppose this object is a constant, simply a constant. So then this becomes simply the integral of J0 or J0 at infinity. Psi is a constant, so it gives you the charge. If psi is a constant, this term will go to 0 in QED, and this will give you the electric charge, which very often we write as E dot ds at infinity, and E dot ds is a flux at infinity. But of course, E dot ds in quantum classically okay, but quantum field theory has no meaning because you are taking a distribution and multiplying it by test functions, which is not the proper test functions for this operator. So if you try to operate it on a quantum state, you will get nonsense. You can try doing the calculation, and you will get all kinds of undefined objects when you do that activity. Okay. So this is a review. Now I will go into my the heart of my matter. So I want to start with uh, with the standard QCD Hamiltonian H0, which is a full standard QCD Hamiltonian, which is normally written as the integral of E square plus B square integrated trace plus the interaction with matter terms, okay, and that will be the full Hamiltonian or the standard QCD Hamiltonian for which you prove things like asymptotic freedom. Okay. So it will be the full gauge theory Hamiltonian with, and it has no chemical potential. Okay. Now we know that for example in QED we can add there is a chemical potential which is the integral of J0 integrated, which is a number operator. But the number operator is a gauge U1 operator generating the U1 gauge transformation. So the chemical potential in QED is actually the generator of a U1 transformation. So with that fact in my mind, I will think of the generator of gauge transformations. So I forgot to say something. In case the psi does not vanish at infinity, so there are two cases of Q. When the psi, the test functions vanish at infinity, these operators vanish on the quantum states, and these are nowadays called small gauge transformations. When psi does not vanish at infinity, so this need not vanish on the quantum states. They are called large gauge transformations. These are the objects for which there has been a great many papers trying to derive low energy theorems and so forth, and we will see how they emerge. So when I say that psi does not vanish at infinity, I am dealing with what people call as large gauge transformations. There is no reason why they should vanish. Okay? But I don't do partial integrations. I don't try to write it as surface integrals, because that, in my opinion, makes no sense in quantum field theory. Classically maybe, but in quantum field theory they make no sense, to me at least. So once I tell you that psi vanishes and q psi vanishes, the standard Gauss law, I give you the standard Gauss law where q psi vanishes, where test function is vanishing at infinity. I can do a GNS construction on the given quantum state, and I can recover the full Hilbert space from the quantum state I am given. Okay? So that there is a canonical procedure we can do that. If in case, but there are, of course, depending on where you start from, there are many different quantum states. I should say one word. When I say quantum state, I mean state is a what is it? A positive operator valued so is a probability. It gives you expectation values of operators when you evaluated omega, what we call density matrices. But what I mean by quantum state is a density matrix, and there are many inequivalent density matrices. And so if you take a quantum state which is appropriate to charges not vanishing at infinity, you will get a different density matrix. And when you do the JNS construction and recover the Hilbert space, you will get a different representation of the operator algebra. So there are many different layers of the quantum of the state of the operator algebra representation, and they are the inequivalent representations. So now I come back here. Okay. The H0 is a standard full Hamiltonian, and when you do standard analysis, they will generate for you the standard differential equation for the evolution of the field operators. So you get the standard local equations for the operator, for the observables of the theory, and we know that that evolution equation is globally hyperbolic. Okay? So it generates, it preserves causality, preserves all the nice properties. There is no, and you can do perturbation theory on that, and you will get asymptotic freedom. All those things are okay. Now what I will do is to add to this mu H0 some q psi. Now the psi need not vanish at infinity. Okay? So I will add q psi to H0 with some scale mu. Okay? This object here H1 will commute with H0, because as I told you earlier, this operator here commutes with all local observables, and it also commutes with H0, which is actually E square of local operators in some limiting sense. Okay? So they will continue to commute. It is a statement that H0 is a gauge invariant under Gauss law, okay, which we are familiar with, which in this case can be proved quite rigorously. So I will add this H1, and this H1 will commute to H0. So what is the consequence? Since they will commute with H0, it will not affect local equations at all. Okay? So the adding of the H0, H1 to H1, H0 will not affect local equations. You will not see it in local analysis. You will not see it in asymptotic frame. No nothing. Okay? But I will add H1, and they will it's like adding a chemical potential. So it will affect the further calculations as I will show you. Here, after we had discovered this, my friend Parthasarathi pointed out that he and Anishati have written a paper where they have added such a term in finite temperature field theory of QCD. So I have given the reference to that. In fact, they added some analog of Q and called that the chemical potential, and added it in the context in their analysis of finite temperature field theory. Okay? So I should mention that immediately. Okay? Now I will later. I don't have time here. I should say later. There is an interpretation of. So let me just say here. This Q psi is operative at infinity. It's an equivalence class. If I add to Q psi terms, Gauss law, like small gauge transformations, you will not see anything. Okay? Because adding to Q psi small gauge transformations will generate another Q psi. Okay? Psi is only defined up to what happens at infinity. Okay? So you can add any terms where the test functions are vanishing at infinity. So this Q psi is a member of an equivalence class, infinite dimensional equivalence class. Okay? So because of this fact, this H1 is some operator which really is acting at infinity. Okay? So, but it is not a split extension. That is, so you have an equivalence class and you are quotienting it out by all terms vanishing at infinity. So you may think that I can take a section of this sequence, but this is not a split sequence. Okay? So you can't do it. If you do it, you will get, in the context we are dealing with, one will get undefined objects, and then you have to mess around. Okay? So I don't want to do that. So it is an equivalence class. That is how I want to treat it. Yeah? Okay. So because this object is acting at infinity, it is. I have done the work here to try to interpret this the asymptotic value of psi as a coupling to laboratory, some experiment. Okay? People say about things like collapse of wave packet. I don't think that physics consists of two theories. One is classical and one is quantum. And when you make an observation, things collapse. I don't think this is correct. Okay? In fact, I don't think of the modern literature thinking of this as the correct thing. And already long ago, Klaus Hepp has pointed out how he has made a model where you can detect what is happening in the bulk by events which happen at infinity. He has given a model where the coupling of the experiment at infinity registers the events in the bulk, and subsequently there have been papers along this line. Lanzmann, for example, has talked about borification, where he passionately argues that one should not talk about, people don't talk about collapse of wave packets. That is a wrong way out. There is no collapse of anything. Okay? It's just that a classical, but the commutative algebra emerges naturally at infinity. When the commutative algebra define classical systems, effectively you get Bohr's limit, and there are now models which are being developed on how to couple the laboratory, which is quantum, to the to the quantum system and how this coupling is registered by events that are happening in the laboratory treated quantum mechanically. Okay. So let me go on. Okay. I want to finish. Okay. Okay. So these Qs, by the way, generate in the QCD fulfill the standard algebra. The commutator of Qs, two Qs, has this property. Okay? And because it is non-abelian, I am doing with QCD. We know that and they commute with all local observables. We know that we can, in a given irreducible representation, I can only diagonalize a complete commuting set. Okay? So in QC, let me take for a illustration cases where this the asymptotic value of the test functions at infinity are constants, spatially constant. So at infinity, we think of the infinity as a two sphere. On the two sphere, these are constant functions with values in the Lie algebra. Okay? So let me take that case. Then let me see. Okay. So I will diagonalize a complete computing set of these operators, okay, and see what happens. Okay. The complete computing set is in abelian algebra. As I told you, abelian algebras play an important role, and the complete computing set is an abelian algebra. So in our case, you can take the abelian algebra. Okay. I am getting now not very clear on how to. So let me consider the case where the psi at infinity is a linear combination at infinity is a linear combination in SU3 of the third component of what we call isospin, okay, and hypercharge. Okay. So it is a third component isospin and with coefficients which are constants at infinity. Okay. So I consider a particular Q which is of this character. Okay. So I will diagonalize my quantum states with this operator as a diagonal. Okay. So I diagonalize. So this is corresponding to a particular irreducible representation of the QCD, where third component of in color space, the third component of isospin and hypercharge are diagonal. Okay. Now this is for the quantum state, vector state. But the H1 I added to the Hamiltonian need not commute to this. I can add anything which is a large gauge transformation. If it is a small gauge transformation, one is wasting time because they will vanish on the quantum states. But if it is a large gauge transformation, I can add anything I like, and then they may not commute with what I have diagonalized. In fact, they don't. So that is what I want to say here. Okay? So this is a new feature. The H1 I am adding to the Hamiltonian, what I call chemical potential, need not preserve the diagonalized quantum state. So that necessarily changes the supersolution sector, and that will mean necessarily QCD is broken. Okay. So let me finish off. Okay. By the last few remarks, I make overflow by a few minutes. Okay. So let me do that. Okay. So let me see why this implies color confined and color deconfined states. Okay. So it will not be confinement in the sense of Wilson lines. Okay. As I say, I am not doing functional rigors. Okay. I am not thinking of two classical charges which are very heavy and then seeing how the potential is changing as I separate them, because I have no classical charges and there is no potential. This is a quantum field theory. But the result I get lead to a related result. Okay. So let me see what will happen. Okay. Let me look at a particular case where lambda 3 and lambda 8 are diagonal. Okay. So the quantum state I am dealing with these are diagonal. There are 3 quantum states possible. and their linear combinations in the diagonalized Hilbert space state, which will define the domain of the operators. Okay? Okay. Now, the picked H1 I have is commuting with what I have diagonalized, everything is fine. Okay? But there is no reason why they should be commuting. So let me take H1 which does not commute, then with that I will stop. This is a generic case. I call them chemical potential because they play this, they are also gauge transformations as is the chemical potential, standard chemical potential. So I will take the linear combination of lambda 1 and lambda 8. Lambda 1 will not commute with the diagonalized lambda 3, and I will choose this mu 1 and mu 2 to be the coefficients to be irrational. So the periods, because mu 1 and mu 2 are irrationally related, the period of this H1, exponential IT H1, it is irrational, so it will never close. It will be ergodic. It will be ergodic in the groups in the Cartan subalgebra space I am dealing with. This is what will happen generically. And mu's will set the scales of the problem. So now I see I have a diagonalized complete commuting set, and since lambda 1 and lambda 8 are, if I take the vector state where the only hypercharge is excited, the third component, then because this lambda 8 is already diagonal here, nothing much will happen. It will just give you a phase times this operator. So that will have a period pi over mu 8. Okay. So here there is no problem, there is a period, the state is changing in time, but the expectation value of a colored observable will be periodic in time, and I can deduce them, I can tell what it is by looking at it. I will come in a minute to this back. So it will be a finite period which I can find out. The period is pi over mu 8. But look at the other two cases. The other two cases will be, both these terms will be operating simultaneously and they are irrationally related. So if you go on changing in time, because of the fact that the ratio is irrational, the orbit will never close. Okay? That will mean that a quantum state I am picking will have an orbit which never closes. This is quite similar to, the phenomenon is quite similar to what happens if you take a torus and you have the real line act on the torus. You get this ergodic action of the real line on the torus which never closes. This is a phenomenon of this kind. However, it is in the context of Lie algebras, compact Lie algebras. I am quite sure, but I don't know the literature, that people doing sister dynamical systems have studied this. I don't know the literature, I have not found the appropriate definition, but it will not close. But in any case, the point is that if it is ergodic, and I look at some color expectation value of any colored observable, any colored state, for example, it could be a color of one of these large gauge transformations, which I think of as an observable and take the expectation value. We remember that the strong interaction time is about 10 to the power of minus 23 seconds. No experiment will check things in this time interval. It takes an average of the observable over this time interval. So you can average, because of the period, here you have an ergodic action, so I had to average the observable I am looking at over this time period, and I will get 0. I will get 0, just like in the stand. So if I get 0, I will not see color. So this will be a color confined state when the action is ergodic. In the other case, it is non-ergodic. You can depending on the period that is involved, it is more accessible. I will be only partially integrating over some fixed period. So there is no reason why the expectation value of color over one finite small period should be 0. You will get some value and you can deduce perhaps what the color is of that state. So that will be the case where color is deconfined. So both these cases are possible. The full analysis of this system has not been made. I will tell you the problem, then I will stop. So I have given you this is one of the problems which come here. This is the case. Is it true that the color deconfined phases where the orbit I am looking at has a finite period, are they in some sense attractors for the other ones? This is what I would expect for a dynamical system. How do I deal with that case here? This is not a dynamical system of the classical kind. How do I deal with that case here? I don't know. This is something worth thinking. How do I check that small disturbances of the color deconfined phases will bring them back to the original deconfined phase as time evolves? Can I prove this fact? I don't know. That will be very interesting, but I don't know. But there is a more difficult problem which I should say, then that is my last statement. Yeah. One moment. Where is this? There is this term, this thing with H0 and H1. Yeah. So, this is an issue which I don't know how to handle. Okay? The reason is, I said that this H0 and H1 commute. This is only a formal statement. Okay? What happens actually is that this large gauge transformations which change the supersolution sectors are what we call anomalies. Okay? They are exactly like gamma 5, the chiral anomaly is exactly anomalies. So I am arguing that in QCD there are an infinite number of anomalies of this operator. So if you write effective field theory, it should respect all these anomalies. Okay? People do not do that. They only take chiral anomaly and Etrof's conditions, but in general that is not the case. Okay? There are infinite number of them. Now this H1 I said commutes with H0 because H0 is consisting of local operators. This is only not quite right, because what happens if I look at actual models, okay, is that this H1 changes the domain. H1 exponential of IT H1 acting on quantum state changes the domain of H0. Okay. This is how the experiment did the action of H1 on the quantum state is registered in the local observables. So it changes the domain. Okay. For example, a charge neutral state can become charged state as time progresses. Well, it is an illustration of the kind of things I am saying. So it can change the domain. But if the domain is changed, it is not correct to say that H0 and H1 are commuting. That's only if you do calculations on a piece of paper without worrying about domains. If the two domains are such, so if the domain of H0 is changing all the time, the time evolution generated by H0 is no longer exponential IT H0. How do I deal with that? This problem already came up for very simple systems like particle on an interval with boundary conditions at the two ends, which are changing in time. Okay? Apparently, people have done experiments of this kind, and this has been treated already by Trotter in his original papers. Okay? And you have to deal with domains of quadratic forms and do things with that. Okay? The theory of quadratic forms are something I am not very familiar with. The domains of quadratic forms can be much larger, and there is a prescription on how to deal with these objects. But I am not familiar with how to, the mathematics, the arguments involved are not so trivial. But in the case of the finite interval, it has been proved by my colleagues, Paolo Facchi, Beppe Marmo, Manuel Vasori. They have written paper, and Alberto Ibot. They have written papers where they show that for a particle on an interval, if you apply this time evolution where the domains are changing as time is progressing, rapidly changing in time, then the limit point of the after some evolution, the fixed point are directional boundary conditions. Yeah. They prove it, energy is not conserved in this process. They prove it using the theory of quadratic forms. I don't know how to adapt it, their arguments here. I would say that is an open problem. So this analysis has to be revised as time progresses. I think I'll stop here because I have overstepped by 5 minutes. Thank you. Thank you.